Great. So to motivate this work, we often don't see legged robots being used in mission critical settings. For example, this Mars rover over here has wheels, even though it limits the platform to regions with relatively flat areas, and we couldn't send the rover to more steep areas like these cliffs in the background. Legs, on the other hand, offer more adaptability to the given environment, as you see in this video, where Spot is able to climb up this rocky terrain. So why aren't we using legs in these mission critical settings if they can broaden the searchable space? So one reason is because legged robots are not reliable enough. Legged systems are less reliable partially due to the discontinuous nature of impacts that are made during locomotion. In this example, one small slip leads to a drastically different outcome than planned. In the case of wheels or other systems with smooth dynamics, these smaller perturbations lead to small differences in outcome. To increase the reliability of legged robots, they must be able to plan robust global trajectories and be able to efficiently reason about these hybrid dynamics that arise from contact. I've organized my approach in 4 different ideas. One way to deal with uncertainty is to plan trajectories that avoid the growth of uncertainty or even possibly shrink it. In this example, even though the shortest path to get on top of this ledge is to maybe walk over it or jump over it, but it might be more reliable just to take this longer route and walk around this ledge to get to this location. The ledge route is inherently less reliable because of the varying contact conditions that are made to traverse it. However, if you cannot just avoid these riskier regions, we still need to be able to traverse them. Planning for contact systems is again made difficult due to hybrid dynamics, where hybrid dynamics are when you have different dynamics in your system, and they can also have discontinuous jumps. For example, when a robot's foot is slightly off the ground, the robot cannot apply any forces but to the ground, but when it's slightly lower and touching the ground, the robot can apply as much force as it is able to. Because of these discontinuities and nonlinear continuous dynamics, planning for these systems is not efficient. This may not be an issue if we could plan a variety of behaviors offline, but these behaviors will not directly adapt to new scenarios. So for example, in this case, the robot's legs are stuck and this ultimately led to its failure. The robot should not be trying to track its nominal pre-planned trajectory, but rather it should create a new one which accounts for this new situation, with its back legs being stuck behind the ledge. In addition to being able to replan in real time for reliable control, it is also essential that the robot has an accurate estimate of its state in real time. Again, the hybrid dynamics hinder state estimation methods, and many of which that can deal with them need to be ran offline. Without an accurate estimate of the state at each control loop, the system will not be able to track well and could ultimately become unstable. In this example, with an accurate state estimate, which reasons about the hybrid dynamics, you could possibly in the future figure out that the foot slipped, which could inform the robot to plan a new behavior. So here's an overview of this presentation where the corresponding sections are being highlighted at the top. First, I will briefly talk about creating robust trajectories through convergent planning. Then I will give a background on linearizations about hybrid transitions. Next, I will discuss my work in utilizing this linearization for efficient state estimation and planning. And lastly, I show results on using this efficient planning for model predictive control. Overall, I will start with more theoretical simple examples and background, and then go into more complex robot examples. In this section, I will give a high-level summary of how to plan trajectories which are robust to state uncertainty. For more details and results, check out chapter 2 in my thesis. Typically, we would make a system more reliable by closing the loop around the robot states. However, in the case of mobile robots, they're often underactuated and undersensed, and therefore cannot fully close the loop. One example of an undersensed robotic system that we looked into for this work is a mobile robot on a hill tasked to traverse from its current position to a goal region with no GPS. The robot will only have a rough understanding of where it starts on the hill, but it has precise heading control and an accurate map. We give the robot a heading with respect to the local hill gradient at each time step, and the robot's controller defines the dynamics of the system. In this setting, 2 drastically different situations may occur if you give a constant command to the robot to go uphill, so facing the hill gradient. In the case on the left, if you're slightly off of your planned trajectory, neighboring trajectories tend to spread apart and expand your uncertainty. And you see the neighboring particles over here. However, if you are slightly off on the trajectory on the right, the uncertainty reduces over time. We would label the trajectory on the left divergent and the one on the right convergent. In this work, we utilize contraction analysis and trajectory optimization to create convergent trajectories. Here is an example problem setup where if we start at this location on the hill, And if we plan a minimum energy trajectory, which is a straight line, we would diverge a lot more if we would take the slightly longer route. So this is really evident in the end distribution on this right figure, where if you take the shortest distance, it expands your uncertainty, where you shrink your uncertainty to this line with this optimal trajectory. So when planning under uncertainty, we have to consider how the dynamics of the system will affect uncertainty growth and ultimately the success rate. However, contraction analysis only applies to smooth systems and not for hybrid. There's been work to extend contraction analysis to hybrid systems by utilizing linearizations about hybrid transitions, but the results are a little too conservative to be directly utilized in my framework. However, these linearizations are still useful for creating hybrid methods, and I'll give a background on them. So in this section, we are talking about linearizations for hybrid events. The linearization is called a saltation matrix, and it is a crucial mathematical tool that we use in all the hybrid algorithms that we created. But first, I need to define a hybrid system. Informally, a hybrid system consists of different hybrid modes. And in this case, I chose I to be the current mode and J to be the next hybrid mode. Each hybrid mode has its own domain, dynamics on the domain, and hybrid transitions are triggered by hitting a guard surface and transitions to the next hybrid domain through a reset map. So for a rigid body system with context, mode I could be a leg swinging freely in the air. The guard is a distance from the toe with respect to the ground. The reset map is the plastic impact law for when the toe hits the ground. And mode J is when the toe is in contact with the ground. So here's an example hybrid execution where a particle starts in hybrid mode I, flows with the dynamics on I, hits the guard, resets, and flows with the new dynamics on J. So an important question to ask is what happens to neighboring particles that are delta x away? In this case, suppose t minus is the pre-transition time and t plus we'll later see is the post-transition time. Again, we flow with the dynamics on mode I, hit the guard, reset, and flow with the new dynamics on J. But is there a way we can formalize what delta x t plus should be given delta x t minus? So this is what the saltation matrix captures. Ultimately, the saltation matrix is the update for the sensitivity equation during a hybrid transition. So basically, if we have our initial perturbation delta xt minus, the saltation matrix describes how the original perturbation is transformed into the final, which is delta xt plus. So what makes up the saltation matrix? It is the Jacobian of the reset map, plus an outer product term that captures variations in the differing dynamics as well as in the guard. It's important to note that sometimes the Jacobian of the reset is used instead of the saltation matrix, but this is incorrect. Even though the outer product term only consists of one rank, this difference can be large. So what else can we do with the saltation matrix? We can use it to propagate covariances through hybrid systems as well. Suppose you have a distribution with mean mu and covariance sigma. The mean, of course, gets mapped using the reset map, but how does the covariance exactly propagate? So similar to using the Jacobian of your dynamics to update the covariance, the saltation matrix plays an analogous role. We see over here, instead of having a DXF term, we have the saltation matrix instead. So I validated this covariance propagation law by simulating particles through a hybrid system. This simple hybrid system best highlights this, where the dynamics in each mode are constant, the guard is a straight line, and the reset map is an identity transform. And you expect these constant flows to not affect the covariance, nor should the identity reset map. However, the differing dynamics at the boundary does. So if you only apply the Jacobian the reset map to update this covariance, see this red dash circle, we would get the incorrect update. Whereas we know that using the saltation matrix, we can correctly propagate the covariance and get the correct covariance estimation. So I tested this covariance propagation law on several hybrid systems in addition to the constant flow system. I analyzed a bouncing ball system where again, the Jacobian, the reset map does not capture this change and looks very incorrect. I also applied this to a pendulum system where a pendulum can hit a spring damper at the origin. And just like the other examples, the saltation matrix captures the propagation better than the Jacobian, the reset map. And lastly, I applied this to ASLIP, where the reset map is switching from Cartesian to polar coordinates. And I didn't show a 2D representation for this example because it's a high degree of freedom system, and there isn't a great representation of it. However, for all of these cases, I use this table over here where we use the estimated covariance and compared it against the actual using KL divergence, where the lower the KL divergence, the better they match. We see here that using the Saltation matrix for each case leads to significantly better estimating of the covariance. Next, I want to talk about the Saltation matrices for rigid body systems with contact and how variations get mapped through these systems. So in this simple example, we have a planar point mass dropping onto a slant parameterized by an angle theta. When the ball makes contact with the slant, plastic impact is applied and the slant imposes both a position and a velocity constraint, which states that the ball cannot penetrate the surface. So right away, if we were to think about using just the Jacobian the reset map, it wouldn't be enough because plastic impact affects velocities and not positions. And we will see that the Saltation matrix captures these variations in position terms correctly. So to best illustrate this, we flow a distribution of particles, and we see that the Saltation matrix correctly updates the variation for position. Notice that the Saltation matrix is eliminating any variation away from the constraint surface. So if we zoom in on the Saltation matrix for this example, it consists of a repeating block diagonal component which defines the velocity constraint. This makes a lot of sense because the position variations will map the same way as velocities, and it is vital information to provide algorithms which utilize this information. Overall, the structure for this simple example is really interesting, and the Saltation matrix is capturing a lot of information. Similar structures appear for generalized rigid body dynamics with unilateral constraints, and for a detailed derivation and explanation of these generalized Saltation matrices for these systems, see chapter 3 in my thesis. So the main takeaways from this section is that we can use the Saltation matrix to map perturbations and covariances through hybrid transitions. The Saltation matrix updates the variations for position through contact, and you should not substitute the Saltation matrix with the Jacobian the reset map. We will show more results later on what can go wrong if you make the substitution. So in this section, we apply the mapping covariance results to create a hybrid Kalman filter that can run efficient hybrid state estimation. First, I'll explain the hybrid state estimation problem. For this problem, we assume that we have a model for the dynamics in each mode, a model of how the states reset, location of the hybrid guards, and a measurement at each time step. So previous state estimation algorithms lack the ability to altogether handle nonlinear dynamics, guards, reset maps, and also all be ran in real time. One example is using a hybrid particle filter to maintain a belief of all probable states. However, to keep an accurate estimate of the state, it requires many particles, which is not feasible to be ran in real time. Overall, we want to be able to maintain an accurate estimate of the state given noisy measurements and handle nonlinear hybrid dynamics all in real time. So a popular fast state estimation method for smooth systems is a Kalman filter. A Kalman filter maintains a Gaussian belief of the state and updates the belief using the dynamics of the system, and each time a measurement comes in. For clarity, we assume these time steps coincide. So the process update uses the dynamics to update the mean and covariance. We see over here that the mean and covariance update law uses the dynamics, and when a measurement comes in, the update compares the belief against the measurement in an optimal fashion. So a traditional Kalman filter will work on a hybrid system, except for when a hybrid transition occurs. So what happens when there are hybrid dynamics? Well, we can use the update law that we defined before when we were talking about mapping means and covariances through hybrid events. So specifically, if the guard is hit during the process update, we apply the reset map and then simulate the new dynamics for the rest of the time step. Then we apply a sandwiching technique to capture how the covariances are propagated throughout the old dynamics, the hybrid transition, and then the new dynamics. So for determining if the guard condition is hit, we integrate using an ODE solver with event detection. And I removed the process noise from this covariance update just for clarity. So if the measurement drags the mean through the hybrid guard, then we simply update the belief using the hybrid update law. So I named this algorithm the Salty Kalman filter, or SKF for short. I validated the SKF against a 2000 particle hybrid particle filter and compare the SKF versus a different variation of the algorithm, which uses the Jacobian the reset map, which I call JRKF here. So I simulated 1,000 runs of the system and compare the error between the different methods. On the top, I show one example run, and on the bottom is the mean absolute error for each time step for the 1,000 trials. So before a hybrid transition is made, all methods are comparable, but when a hybrid transition occurs, the GRKF suffers due to its incorrect update law, and see that this red dotted line has a higher absolute error. Whereas the particle filter does slightly better than the SKF near the hybrid transition, and I believe this is the case because the hybrid particle filter actually maintains the split distribution rather than the SKF, which updates the belief all at once. However, when comparing the runtime, the SKF is statistically indistinguishable from a 1,000 particle hybrid particle filter at the fraction of the runtime. So I also validated the SKF on a more complex system where the ASLIP system is the one I tested against, which I showed earlier. We see similar trends. The SKF did statistically better than a 30,000 particle hybrid particle filter. However, I believe with enough particles, the particle filter should be better than the SKF. Though increasing the number of particles for this experiment would increase the computation time, and it would not actually be feasible to be to run this experiment. So overall, the SKF performs better than using the Jacobian of the reset map, which we predicted from the previous section. And like an extended Kalman filter, the SKF depends on local assumptions and breaks apart when these assumptions are also broken. So it does not explicitly reason about the probability of transition. So if your mean is closer to the guard, the algorithm thinks the probability is the same as if your mean is far away from the guard. This could lead to issues later and should be looked more into the future. Next, I will be focusing on the dual problem, which is planning and control for hybrid systems. So in this section, I talk about planning trajectories for hybrid systems. First, I want to give a quick background on iLQR. So iLQR is commonly used to plan trajectories in real time and has been widely successful for creating dynamic behaviors for continuous systems such as drones, but does not directly map to systems with discontinuous jumps like our legged robots. iLQR first starts with an initial guess for the inputs. Oftentimes we do a simple trajectory or zero input is chosen. So this UK would equal 0 for each time step. This initial guess is simulated forward using the system's dynamics. A quadratic cost is evaluated based on how much input is used and how much tracking error there is. A backwards pass is done by linearizing the trajectory at each time step and creating a local control policy which contains a feedback and feed forward term. This new policy is then implemented on the forward pass, where again the system dynamics are simulated and the feed forward gains are scaled through a line search. This cycle of backwards and forward pass is repeated until convergent. To further illustrate this algorithm, I show an example trajectory generation for a pendulum swing up. So this animation is showing the different components of iLQR in state space. The rollout is shown in black. The backwards pass computes the direction of improvement and creates a new control policy. The forwards pass uses this new policy to improve, and again, this cycle is repeated until convergence. So note that the red arrows are shrinking after each iteration, and once they're sufficiently small, it means that iLQR has converged. So how does this change when we have a hybrid system? Well, the general problem setup is the same where we have some start state and a desired goal state. We still want to find the states and inputs that minimizes some cost. However, now the dynamics can change along a trajectory, and there can be sudden jumps in the trajectory, such as from plastic impact, where the toe velocity instantaneously goes to 0. Standard iLQR, as well as other standard trajectory optimization algorithms, cannot handle hybrid systems due to the differing modes as well as the discrete jumps. And trajectory optimization algorithms, which can handle these jumps and differing dynamics, such as contact implicit trajectory optimization, are very difficult to compute because they are inefficient due to the combinatoric complexity of the constraints. So how do we handle these issues that arise from hybrid dynamics? Well, we can make several hybrid modifications. So first, the hybrid dynamics need to be simulated. The backwards pass must be updated to reflect these changes from simulating the hybrid dynamics, and mode mismatches must be handled correctly when we apply the new control policy. So when simulating hybrid dynamics similar to the SKF, if the guard is hit in the current domain, then we apply the reset map and then simulate forward using the new dynamics on the new domain. And on the backwards pass, as an approximation, we linearize only about one of the hybrid dynamics. And this approximation is arbitrary, but leads to a piecewise smooth control law, which helps with convergence. Then I use the Saltation matrix to update the linearization about the hybrid event. Lastly, since the hybrid transition can move around due to simulating a new control law at each cycle, an issue may occur when the current hybrid mode does not match the reference. This issue can be locally patched by extending the references to ensure there is a reference for the correct mode. And for the input, we can just hold the input and gains constant during this time. So by applying these modifications to iLQR, we extend it to work for hybrid systems. So in this simple example, I have a bouncing ball which has a thruster on it in the vertical direction. The ball wants to get to this dashed line ending with 0 velocity. So for this first example, I show hybrid iLQR seated with 1 bounce, and we can see that the gradient information is actually moving the contact time to fully utilize the impact timing. So I'll let this run a little bit. And then we converge to the solution over here. So in this next example, we have the same exact problem, but we give the optimizer a bad seed of 3 bounces when it only needs 1. However, the algorithm is still able to find the same 1 bounce optimal trajectory that we previously saw in the example on the left. So overall, this example demonstrates the algorithm's ability to move and remove contacts to produce optimal trajectories. So I compared using the Jacobian of the reset map versus using the Saltation matrix for several different systems. Over here are 2 examples where, again, this is the bouncing ball example that I just showed. And then the example on the right is a quad rotor, which is tasked to perch in this goal location over here, and it can make contact with this curved surface. So when using the Jacobian of the reset map, the end position is actually this red circle over here. It comes up with a very erratic trajectory and doesn't converge. Whereas if we use the Saltation matrix and the rest of the algorithm, we're able to find a good solution, which is this one highlighted in teal. So lastly, we're able to use hybrid iLQR to produce a long jump for a full order planar monoped robot. These results are really cool because the algorithm is able to move around the context state and timing, which is something we couldn't do before with standard iLQR. So overall, our hybrid iLQR method has some strengths and one noticeable drawback. Its strengths are that it is able to efficiently plan out a hybrid trajectory due to linearizations. It always returns a feasible trajectory because it is a shooting method. And we also provide stabilizing gains about these hybrid trajectories. However, when you encode the complementarity constraints through simulation on the forward pass, it becomes very dependent on its initial seed. It is not able to explore or add contacts easily because there is no gradient information for these new contacts until we have discovered them. For the remaining results, I will no longer compare the Jacobian of the reset map because it's just clearly not the right answer. So in this last section, I propose a method for reliable hybrid control. So suppose we have a hybrid trajectory already planned out and we want to be able to track it. The question is, what do you do when the robot is quite far away from the plan due to uncertainty or perturbations? So using the hybrid extension fix when mode mismatches occur might not work well because this is just a local patch. However, by using the extensions in this scenario, the robot can lose a lot of energy and could ultimately not make the jump. Instead, what we would like to do is replan a new trajectory, which is similar to the plan, but allows the robot to make use of different contact timings and locations. So we can utilize hybrid iLQR to replan this trajectory. We can create a new trajectory which would be able to move the contact timing and location here such that we would plan a new trajectory which we can still make the jump even with this large perturbation. So one benefit of iLQR or any other shooting algorithm, like I said earlier, is that we always produce a dynamically feasible trajectory, and we don't have to wait for optimality to use it. So this is very important for a model predictive controller to return a dynamically feasible trajectory if terminated early. So once a trajectory is replanned, any small perturbations can be stabilized by the feedback gains calculated when creating this new trajectory. So next I will go into some necessary fixes to run hybrid iLQR as a model predictive controller. So one of the main aspects that is needed to be addressed when going from hybrid iLQR for trajectory generation to tracking is evaluating the cost when there is a mode mismatch between the solve horizon and the original reference. Excuse me. To highlight this, we will go back to the bouncing ball example where we have generated this trajectory and we want to track it. So if we disturb the trajectory far enough from the nominal, the optimal impact timing will change. In this animation, the original trajectory is this black curve. The reference for each time step or horizon is highlighted in red, and the current MPC solve is this blue dashed line. So at each time step, we are solving a 50 time step horizon problem and using the first input. We'll see that the MPC is tracking well up until the target horizon hits the ground. And due to the reference and current horizon being in a different mode, there's a very high penalty, which causes the solver to use a lot of energy to reduce the state error rather than using the natural dynamics. So to fix this, we can apply a similar fix as we showed before for extending the reference for feedback. For this work, we pre-process extensions for the reference trajectory by simulating past the guard and simulating backwards post-impact. So now these extensions can be used whenever there's a mode mismatch along the current solve horizon. So with this change, the algorithm converges more often and the solution makes use of the hybrid dynamics rather than trying to force the cost to lower by applying large inputs. This is especially important for underactuated systems that cannot afford to spend a lot of actuation to fix large errors in state. So the difference between not using the cost update and using it is quite large when looking at the input space. In this plot over on the left, the reference input is shown in black and the actual input is shown in blue. And this green region over here is where the solver sometimes did not converge. When using the cost update, the input used follows very closely to the reference and converge for every single time step. For tracking, it's important to update the cost because these large state errors propagate into the backwards path and create bad solutions. So next, I will talk about using hybrid iLQR MPC for stabilizing a quadruped robot. So in order to run this on a full order robot, we use a hierarchical control stack where here's a block diagram showing the structure of the control stack. The robot state is being sent to both the high-level MPC and the low-level feedback controller. Trajectories are constantly being planned and sent to the low-level controller to track. To get this algorithm working on a 3D legged robot in real time, I used a dedicated robot simulator, which has the capability to parallelize the forward pass computations. And I also utilized efficient analytical derivative computations of the rigid body dynamics. So here's an example of hybrid iLQR solve for tracking a backflip. This clip is showing off the parallelization of the forward pass as well as planning dynamic whole body motions. So in this example, I'm shoving the robot in the beginning of the trajectory, and the robot needs to plan a new trajectory to track the backflip. In this case, it needs to both modify its takeoff conditions, utilize its leg mass and inertia in flight to further stabilize the trajectory, and plan a new landing altogether. So it turns out that parallelizing the line search is very important because sometimes the optimizer needs to take fairly small steps in order to improve. So we see for this example, the line search must take 12 steps in order to significantly improve the cost. However, by parallelizing the line search, I'm able to do all these steps at once and pick the best one. On average, the parallel line search is 2 times faster than doing it sequentially. So for the main results, we focused on perturbations while walking. It turns out that walking at a slower pace is harder to stabilize for because often algorithms rely on repeatedly recycling legs to catch itself rather than planning an intelligent catch recovery. In some cases, a dedicated push recovery algorithm is used separately from the walking controller. For my test, I applied a huge perturbation where I instantaneously add 1.5 meters per second lateral velocity to the robot's body while the robot is walking. see that the robot is shifting the contact time from before and even changing the contact sequence of the other legs to help with the recovery. Note that it only takes one step to recover from this large perturbation. So to get a better look at what is happening with the MPC during this perturbation, I visualize the forward passes that are being computed from the MPC. So leading up to the perturbation, the MPC is returning the original walking trajectory, but once the perturbation is sensed, it replans a new trajectory, catching itself, and eventually it goes back to its nominal walk trajectory. And I'll let this play out a little bit, where we can see it going back to the original walk. So if we zoom into the first solve after the perturbation, the animation on the left is showing all the forward passes for the first solve. In the middle is a Hildebrand diagram of the contact sequence for the walking reference. And on the right is a diagram for the solve where hybrid iLQR MPC is adding and removing contacts in order to better stabilize. We also see very clearly in the video that we are not just optimizing the contact timing, but also the foot location. So next, we want to see if modifying the contact sequence in an optimal way can better stabilize the robot compared to common methods that don't utilize full nonlinear dynamics and uses a set gait schedule. So before I get into comparisons, I need to first explain the compared method. So single rigid body methods have found a lot of success in controlling quadruped robots. The premise of it is that suppose you have a potato and it has some mass and inertia. So our potato has thrusters on its body and it can only turn on every so often, but it can apply a direct force onto the body. So the goal is for the potato to move in space at a constant height. And if we linearize the rotational dynamics, this control problem can be written as a quadratic program where the cost is quadratic and we have linear constraints for when the thrusters can turn on, and they also can obey frictional constraints. Quadratic programs are nice because they can be solved very quickly. This is very useful because the potato model actually translates not too poorly to our robot model, where the robot's body and mass and inertia is the same as the potatoes, as well as the thrusters are now the legs of the robot. A gait schedule is used to enforce when the legs can command contact forces, and these methods that use single rigid body dynamics are very fast and efficient. However, the downsides are that the gait schedule is fixed and the robot model is heavily simplified. So these downsides are made clear by the previous pushing example, where we notice that the single rigid body model method relies on recycling its legs more to catch itself, which in this case, it works out for the robot. And comparing it with the hybrid iLQR MPC, we can see that it takes several more steps and it cycles its legs. But sometimes if we change the contact timing, it actually does not work out well for the single rigid body method, and it can be pretty brittle. So half of the time, the single rigid body method is not able to catch itself. So by changing the perturbation timing very slightly, we see that even though it is able to recycle its legs, it is ultimately unstable. Whereas using hybrid iLQR MPC, it is able to handle this exact same perturbation very elegantly. So I compared hybrid iLQR MPC versus using the single rigid body method for 8 different perturbation times during this walk. So this video represents what is going on this graph. So while the robot is walking straight, I perturb the robot to the left and X marks the position of the robot when I hit it. The red and blue markers are the furthest distance away from the nominal trajectory. So over the 8 trials, the single rigid body method fell 4 times, and when it didn't fall, tended to stray further away from the target. Whereas hybrid iLQR only fell once and was able to come up with very nice recoveries for each push. So after thoroughly analyzing the controller's capability in simulation, I implemented the whole control stack on our hardware. It helps that the lower level controller produced from the backwards pass is very robust to changes in contact. So in this example, I'm just using the local policy created through the backwards pass, which is hybrid LQR, to handle an unplanned 12.5 centimeter tall platform. So in this next example over here, It can even handle unplanned slips as well as getting tangled in its own Ethernet cable. And this is big because this means that if iLQR sends a new trajectory to track, it won't be very brittle to uncertainty in the elevation of its environment or even small slips that happen. So again, we see the single rigid body method does not work well here, where it needs to reason more about the leg kinematics as well as modifying the contact schedule. In this example, we spent a lot of effort in tuning this algorithm to handle this exact case, but we just could not get it to walk down properly. This is the exact opposite for hybrid LQR, where I just use the same exact parameters as I did for the lateral pushing experiment, and it's just able to handle these disturbances. So for a consistent comparison between the single rigid body method and hybrid iLQR MPC, I created a test where we could apply the same exact perturbation consistently and see how the controllers respond. In this case, I blocked the motor commands for the entire robot for 150 milliseconds while the robot started to walk. So the single rigid body method, again, wants to stabilize itself through recycling its legs, but in this setting, it causes it to fall. Whereas the best thing to do is replan a trajectory and catch yourself before you continue. So to further analyze what was going on for hybrid iLQR MPC, we visualize what the robot thinks its state is on the left and what plan it produced at the time on the right. So we are able to see what the robot wanted to do when the motors were blocked, and we can see that it decided to change to catch behavior and then go back into its nominal walking gait. So an unintended disturbance happened caused by turning off the motor commands, where the state estimator actually degraded because it utilized the force information at the feet to get a better prediction of the state estimation. So you can see over here that it's actually sinking through the ground when the motors were turned off. So hybrid iLQR MPC works well for stabilization because it is able to modify contact locations and timing in order to better stabilize the robot. We also utilize the full nonlinear dynamics, which in some cases helps the robot reason about its mass. For a quadruped robot, the legs are pretty light, but this may be very beneficial for robots with heavier limbs such as bipedal robots. We remedy the original issue of local minima by using hybrid iLQR as a model predictive controller, where we can use the original reference as an initial seed. Lastly, it's important to update the cost function when there are mode mismatches to ensure that the algorithm performs well. So overall, in this thesis, we emphasize the importance of utilizing the natural dynamics that occur in our systems rather than ignoring or simplifying them. By doing this, I address several issues of state estimation, planning, and control for legged robots. Specifically, we did this by utilizing contraction analysis to create more robust global plan trajectories for mobile robots and underactuated systems. We analyze how distributions are mapped through hybrid systems and utilizing this information for efficient hybrid state estimation. We developed a new contact implicit trajectory optimization algorithm through utilizing linearizations about a hybrid event. And then we used it as a robust model predictive controller, which solves new plans in order to reject large disturbance all in real time. So the ideas produced from the thesis have branched off into a lot of different interesting directions. First, I'll go through some already completed works from my lab mates, where hybrid event shaping is led by James Zhu, where we use the Saltation matrix to analyze the stability of periodic orbits, which then we use to generalize previous works, as well as we can create open loop stable trajectories for periodic systems. State estimation with uncertain guards is led by Joe Payne, where we looked into state estimation for hybrid systems with uncertainty in the guard location. We augmented the saltation matrix with guard uncertainty terms and applied this to the salted Kalman filter. In addition to those extensions, I think some other potential directions would be great to investigate. In this video, we are able to walk over this large step. However, this behavior could be improved in several different ways. Using convergent planning for contact dynamics would help create a more robust walking trajectory to track. In the SKF, we are not using contact detection to help with state estimation. So finding some way to fuse that contact measurement with the SKF would improve estimation. And lastly, using perception to update the internal model of the environment for hybrid iLQR MPC would allow the robot to interact with its environment a lot more fluidly. So thank you for listening to my talk, and I would be happy to answer any questions.
All right.